here. This is our first event. It's a pleasure to have the first lady in the AIT Journal. And it's a pleasure to have Alice Plebe here. Little biography of her. So she got her master's degree at the University of Catania in computer science before moving to Trento and get her PhD in ICT at the Department of Engineering and Computer Science, working on autonomous driving systems and on the intersection with the cognitive capabilities, working on the European H2020 project for cars. Now she got her PhD in 2021, and she is now a postdoc at the Department of Industrial Engineering, and she will give us today a talk about the current state of self-driving cars and new approaches coming from the cognitive science. She will give her a talk. At the end, you can make all the questions you want to her. And after that, stick around. We have snacks, beers, and drinks, and we can have a friendly chat together. So again, it's a pleasure to have you here, and the stage is all yours.
Thank you, Nicola, for the great introduction, and thank you all for the invitation. I think it's a great opportunity. We have like two severe segregation in our department, and I think this is a great opportunity to meet each other and talk about our research. So I have many things to show you. I'm trying to be brief and clear as possible. And before explaining the works we are carry out in our lab, I think it's important to clear two. Okay. First of all, what are these autonomous vehicles? Exactly what is the definition of this vehicle? And also, I think it's important to clarify exactly how autonomous vehicles are right now compared to human drivers. So, I don't know, maybe you are already familiar with this classification. Basically, we have 5 levels of autonomy. There are actually 6. Level 0 means no autonomy at all. So it's basically the traditional car that probably many people still own. And then we have 5 levels. Just to be brief, basically level 1 means that the system controls either the acceleration or the longitudinal, the lateral control, so it's steering. In level 2, the system controls both, so it can both accelerate and change the lane. But the real thing starts from level 3. Basically, we have this strong separation where from level 2 and below, the human is responsible for driving the car and monitoring the environment. The system, the agent, is basically just an assistant. It just helps the human to carry out the task of driving the car. While from level 3 and above, we have the opposite. Is the system that carries out the task of driving. And we can say that the human is like a supervisor of the system. So in level 3, the car is able to monitor somehow the environment and control the car, but the human is required to be aware of all the time of what the system is doing. So it's like, for example, when you have to keep your hand on the steering wheel and basically not fall asleep, because at any time the system might stop working, ask the human to resume control immediately of the car. It's talking about a few seconds to resume control. And yeah, so basically the human still have to be ready. From level 4, basically the human is not required anymore, except in some cases. I mean, the system can drive completely autonomous way only in selected scenario. Usually these scenarios are highways. Highways are, let's say, quite easy because you have basically only one direction of traffic. The lanes are very clearly marked, and most of all, we don't have usually pedestrians and other stuff in the middle of the road. So you basically level 5 is what actually many people think is autonomous vehicles, meaning is like a vehicle that doesn't have the steering wheel, doesn't have the pedals, because the human is never required. The autonomous agent is able to do it. So, to give you an idea, for example, Tesla in Europe is just a level 2. There are some models that are considered partial level 3, but that's it. Basically, the state of the art is here. Level 4 and level 5, especially the level 5 is something that many researchers I don't want to say impossible, but definitely not in the near future. So let's have an idea of the performance compared to a human driver. The main idea of developing autonomous vehicles is that they are supposed to be better than humans. So they should be safer, optimize many factors like energy savings. But especially, we talk about safety. So let's clarify how unsafe are human drivers. So these data are from 2017, but they stay the same. So we have a minor accident, a human makes a minor accident every 10 million miles, and a fatal accident every 110. So basically, if we want an autonomous vehicle to be better, we should outperform this number at least. But why human drivers make mistakes while driving? The main causes are because they're distracted, they are drunk, they are high, or they make reckless maneuvers. So basically what happens is that when a human driver, an expert human driver, is focused, knows what he's doing, what they're doing, so he's driving well, they overpass these numbers way. So let's give a number for an autonomous vehicle. This is a company Waymo's, the one developed by Google, and basically they reach this number, 30,000. A disengagement means a situation where the system stops working because it doesn't understand the environment, what is going on, or doesn't know how to play. So basically, this is the idea. The record is for 2021, because every year we have the record of year. We are still waiting for the one this year. It usually goes out in March. So maybe the number for 2022 will be slightly higher, but we know that we're still on the degree of science. So this is not at all what we are expecting. I mean, 10 years ago, people would have think that we had completely driverless vehicles and so on. So what is going on? What is not working? There are many things. One, of course, is the problem that the driving scenarios are so variable and often so unstructured that it's really hard to understand what is going on, and also understand the behavior of other users, other road users. So this is, of course, an extreme example, but I think every one of us will be able to carry out a bit, try a bit challenging, but it's not feasible for any drive. But of course, for autonomous driving agent, it's completely possible. So the problem is not just understanding, but also decide the correct behavior in situations that are usually not have been designed during the training. So this video, the situation happened to me. It was my colleague and I, we were driving to Milan. So this is the highway. And we witnessed something like that. I mean, if I have an autonomous vehicle that is, and this camera is focusing on this thing, I mean, this is a question that barriers, I think, they were conceived, so probably could have understand what to do. Actually, this is not what it looks like, because it was a truck getting out another truck that's loaded, so it was the same. So, but from the point of view, it was really, really hard. Okay, so the underlying problem is that the problem of our autonomous vehicles has always mostly been approached with the same method, same parameter. That is the classic engineering one. So it's basically a pipeline of three main elements. That is sense, what the environment around the vehicle, think about what to do, deciding what to do with them. This layout works well when I mean, it's easy, since it's a pipeline, it's easy, for example, when you have a problem, it's easy to understand at which point of the pipeline the problem arises. And also, it works actually really well in situations that have been modeled during the training. I mean, situation that I've already experienced, I know how to drive because I designed like that. The problem is in situations that have not been designed before, that are not specified in the past. And also we have a problem that, especially in the sense think part, we're limited by the symbols that the system is programmed to understand. What I mean is, let me give you an example. So I don't know if you can see, we have here a truck, a van with the back door open and objects are falling out. For a human, it's immediate to understand this now. Answer, this is dangerous, so I will not try to get this button for nothing. But when I fit this situation to a classic sense-impact model, I lost all information because the classes of objects have been hand-designed. I mean, it's sure it's a neural network that does the classification, but I decided in advance to classify between vehicles, lanes, foliage, and so on. So the meaning of this one is completely lost, and I classified just another paradigm that recently has been revised a little bit, the environment. So basically another modern style of architecture. In this situation, you have the advantage, you don't have the problem before that the representation are designed by hand, by the programmer, they learned style the model. However, first you have the problem of training of models because you have to fit virtually every possible situation the vehicle should encounter to actually be sure that the network learns how to behave. And more importantly, maybe, is because you're probably familiar with the problem of black box. It's really hard to understand why some perceptual scenario has resulted in a specific action. And this is a serious hindrance in application, safety critical application, of course, Thomas Driving. So in our lab, we are proposing a new paradigm to approach autonomous driving. It is a community-inspired just a little excursion. If you think about it, driving is a particular application because we already have an intelligent being able to drive really well. It is the human. So why not what humans do and understand what are the possible cognitive mechanisms that can actually improve some of the commonly used approach that we have now. After all, it's the principle behind artificial intelligence to look at a natural intelligent being and try to replicate it. So this kind of paradigm is very close to what happens in the humans because we have these two block, but it's not a pipeline like before. It's a loop. I will explain it better. But there isn't actually a distinct separation in our brain between the perception, computation, action decision. It's a loop that goes back and forth, and the two interact with each other and influence each other. Okay, this paradigm allows us to also learn good behaviors by mental simulation. I will explain it better later. And also it's possible to explain why a specific action has been selected through this principle that I will show you better later. The only problem, it's not the only, but the main one is the fact that our brain is still, for the most part, is still a mystery. So not all the cognitive mechanisms are known, and the ones that are known, they are quite difficult to replicate in hardware and in software that we actually use right now. Okay, I'm talking too much. I have to speed up. So I need to give you a very light explanation of what happens in our brain. This is this diagram, too much details. But the idea here. So, okay, clearly this is the side view of the brain. This is the front. The eyes are here, this is back. And okay, so basically the information coming from the sensory brain, the eyes, are elaborated here on the back. The back of the brain is the most ancient part. The brain, so basically, most mammals have the same structure on the back. The one is more developed, the one is the frontal cortex. Okay, so from the back, the sensory information is here, and it's processed into parallel pathways. The one that is called ventral stream has the purpose of understanding the semantic meaning of the object, while the dorsal stream understands the spatial location of the object. So spatial information and semantic information are actually separated. They are processed into separate. So this is a first thing that we can imitate. Then another interesting thing is that these central information are processed in what they are called cortices. We have a first sensory cortex that is finally processed in the body. So these are topological. They are basically a map containing the information. So I can process partial location directly without direct that's in my mental map. Say. So the motor cortex actually encodes and represents the possible actions that I can perform based on the central information that I get. And then the interesting thing is this loop over here. So basically, all the possible actions are processed by the cerebellum through an inverse model. So basically, in our brain, we have inverse model for basically every possible certain motor behavior that we can carry out. So, for example, if I want to pick up my bottle, before executing the action, my cerebellum will start to look and evaluate all the possible actions in which I can pick up the bottle. And basically what happens is that it's actually predicting also the sensory information that I will receive when I will walk closer to the bottle. So I will actually imagine me walking through the bottle and then deciding which better ways. So exactly. Last thing is the basal ganglia, the central part here, is actually responsible of biasing the action selection process. So basically, with the high level information. So for example, I will have any possible way to go and pick up my bottle. But for example, I know that I'm in a hurry, so I want to be fast. So I'll select the most path to reach the bottle. And this is a way to bias to select the action that I want to select. So for example, I know that there is a problem here, so I want to avoid it. So I go although it's not the fastest way to reach the bottle. Okay, so this is the general idea. Okay, so I will show how all these ideas can be actually inspiration for implementing something similar. Okay, so basically this is our lab, and I present mainly 3 contributions that we do, 3 works that we are carrying out. So first of all, take the cognitive inspiration and apply it to perception, visual perception, and this is mainly my work that I carry out. And then my colleagues, which are mechanical engineers, they are most devoted to the part regarding the motor control. But it's really interesting, so I will talk also about that. Then we have a driving simulator, and I need to make some advertising because probably we need people to perform some experiment with the driving simulator. So if you want to join, and this is the European project which basically I started working with. All this is the results of this, what I do. Okay, so first of all, my part, okay, I have to speed up to make it. Okay, so as I said before, we have 2 streams in the brain to process the sensory information. The ventral one is responsible for the conceptual learning, and the dorsal one that is responsible for spatial learning that ends up in the motor cortex. Okay, so the idea here is to actually concentrate only the conceptual learning and explicitate in an architecture as simple as possible. It's basically an encoder-decoder, explicitate in the latent space to learn specific concepts. In this example, for planes and vehicles. So the information inside the latent space is actually organized. It has a semantic organization. And it's also trained with a LSTM to learn also a temporal coherence. So latent space encoding subsequent frames in a video will be similar to them. this is a visualization of actually the activation of the neurons inside the latent space. You can see in this is an picture that is inside a driving simulator. Basically, we have 4 similar layout of vehicles. There is only one vehicle on the left, and the same lane configuration. And you can appreciate how, despite the significant difference in light conditions and colors and so on, these neurons encoding the vehicle concept and the lane concept are basically the same. The nice thing is that we can actually use this internal representation to do some mental imagery. Mental imagery is basically the situation in which the brain is imagining stuff. For example, if I imagine my dog right now, my sensory cortex right now is activated exactly as my dog was here, if I was looking at her. But I can imagine her in many different situations, poses and sizes, even that are not realistic. And this is basically what we can do with this situation here. And of course, this is useful to learn situations that are not included in the training set. And this is actually a way to predict possible future situations starting from a sequence, starting between sequences. Basically, I'm doing some hallucination on the okay, that was the conceptual learning. This regarding the spatial learning, we can use many 3 principles that are all related. Here I'm talking about attention is the cognitive type of attention. So it's not the attention mechanism that many you're familiar with in the modern neural networks. It's what actually happens in the brain caused by the circadian movements. That basically it's the principle by which if I have to then something, look at something, the center of my pupil, the retina, will always focus on the center of the thing that I'm paying attention to. And what happens is that in the center of the retina, we have much more corresponding neurons processing information. And there is also something called cortical magnification. So basically, I'm mimicking the attention mechanism basically by using the clustering mechanism. If I want to focus only on the vehicles, I will discard all the rest. And the magnification is actually something that happens in the spatial cortex. And here I represented with an occupancy grid map. So basically, this is the ground truth of this scene. Basically, it's a bird's view in which every pixel corresponds to a square patch in the real world, and the pixel is white means that the location in the space is occupied by a vehicle. I know that in the brain there is a magnification still in the center of my retina, meaning that actually in our brain we have much more information coming from the center image. Basically, it's like we have much more pixel here and way less pixel in the external part. So with this magnification, we can mimic something like that. I played with several factors of magnification. The nice thing is that when I push it to the limit, the type of occupancy grid that is still word coordinates, so I can use it to actually perform action decisions. The visualization of this occupancy grid is starting to actually look a lot like what we actually see in the scene. And okay, so again, this type of neural network is as simple as possible, just to test if this, like a proof of concept, if this idea is actually possible to be replicated. And just a nice results here. This is the ground truth. And what happens is actually, you can see here, there is a little bit of a track popping out. And my network is actually seeing it before the ground truth. So it was actually a fun thing. So in the ground truth given by the dataset was not considered this track here, but I never, I don't know how. Okay, so concerning this was the perception part. Concerning the action part, okay. So we are actually proposing to approach the problem in a different way by using the concept of affordance. What is an affordance? An affordance is basically any action that I can carry out in the environment that I'm here. The point is that the affordance is directly linked to the object that I'm seeing in the environment. Give you an example. For example, if I'm seeing a door, I see the doorknob. I have an affordance that this doorknob is actually used to open the door. A dog, for example, doesn't have the same affordance, but if they are still looking at the same doorknob, they're probably perceiving in the same way. But the linked action is not the same, so the affordance is not the same. Actually, in the case of dogs, some dogs actually open the doors, so they are actually acquiring a new type of affordance. So every time they see a new doorknob, they know that they can open the door. So going back to autonomous driving, I can now rethink the way that I perceive the environment in terms of affordance. So that's why I was talking before about the loop between perception and action. So here in this situation, basically what I can do, I know that I am allowed, I'm permitted to drive in all the lanes, basically. I know that I don't have to go outside the lane. But what are actually the affordance? Basically, you can consider three in this case. One affordance might be to stay in the lane where I am. The other one might be to change lane at some point. And another one is if I want to stop. An area here, then we stop. So we start to visualize that set of affordances. We can design an artificial motor cortex that represents all the possible trajectory that I can perform in the environment. So this is our representation of an artificial cortex, where lateral control is the steering rate, R, and the longitudinal control that is the jerk. That is not a bad word. Jerk is the derivative of acceleration. Okay. So basically, this map is representing the three affordances that I can carry out in this scenario. So the points in this map represents instantaneous control that I can perform on the vehicle. So this control over time represents the trajectory gamma that I can choose. So all the trajectory inside A are basically the ones that tell me to don't steer, don't change my acceleration, so go straight. If I want to steer on the left, I will result in the affordance that tells me to change lane on the left, and B is basically to brake and turn right. So this formula here is called salience. Is an evaluation of how good is a certain affordance any. considering the instantaneous initial command J0 R0. So basically, it's a way to evaluate all the possible trajectories gamma that execute a certain affordance, and I will take the best. And B, basically a function to evaluate how good the trajectory is. It needs many information, such as fuel consumption, and so on, but mainly main point is comfort. One thing that is now really an idea that is way granted is that the best comfort is the result of minimal jerk. And for sure you will understand this because I have a high jerk, my car will do steam, so the speed rates to take what makes people throw up in the car. So if you have minimum jerk, you will give something maximum comfort. So this is the science of one affordance. But then how is the agent deciding which affordance to perform? This is made by considering all the sciences for all the existing affordances, weighted by some bias mask. Here you have an example of a bias that is generated by the presence of an obstacle in the lane. So basically what happens is that this obstacle is generating an inhibition on the motor cortex. So basically all the trajectories that will end up in colliding with the obstacle are basically taken out. Their science for is set to 0. There is also a partial inhibition, is basically going very, very, very close to the vehicle. So the overall science is the result of computing of this science for each affordance and weight them with different prices. And here I did one way to be take the max is basically a winner takes all, but it's actually not what we are doing. In the end, we are using a much more refined algorithm that considers the affordances decided in the past, in the window in the past, and also the algorithm takes in consideration that a certain trajectory is shared by more affordances, so we will keep in memory more than one affordance and decide at the end which one to afford. The interesting thing is that this bias mechanism can be used to generate all kind of behavior. For example, this is a very simple mechanism to enforce traffic rules. So, for example, I know that I can't go in this lane from this position, so I will impose a bias mask to avoid to take any of these affordances trajectories. But it can be also a way to influence the agent, for example, to go faster because I'm in a hurry again and I want to go faster. Or maybe I want a more comfort drive, so I will always give a higher weight to the controls in a lower speed and so on. So the nice thing is that in this way, the behavior emerges. I'm not coding explicitly anything. The resulting behavior emerges from the interaction of these elements. And anyway, I'm always able to go back and identify the trajectory, which sensory information decide which trajectory and take. So it's actually an explainable action. Okay, some quick example. I don't know if you can appreciate, but yeah, basically, this is a representation of the salience in 3D. And in this example, we are taking in consideration only the coordinates, basically change the lane, change lane to the left, change to the right. These are web view, top view of the single user. This is the bias mask that will change during time. So in this example, we are merging in a highway, and there are some vehicles already there in the arena. So the agent has detected the car, so it's decelerating to avoid colliding with them, and then he goes back. When he's inside the two-lane highway, it now knows that he can also change lane to the left. So, and that's what happened here. So basically, I'm going to a higher speed than those vehicles. So still, I know that I have to brake because I'm about to reach them. I'm biased to go as fast as possible, so I'm moving to the left lane. And when the other obstacle is going back, resume to the right lane. So none of this behavior is manually coded. All emerges from the way that the mechanism. So here we have a catin, but still the agent here is biased to go as fast as possible. So we will update. And still you can see here the inhibition of the parameter. Okay, this is incoming traffic. Yeah, it's breaking a little bit. Colliding with the crossing car. Okay, at the pedestrian crossing is a little bit. And then there is still incoming traffic, so we will stop completely. And then resume okay, this is the last one, is a pedestrian crossing with a traffic light. And I can appreciate the traffic light is red now, so the pedestrian is not crossing. The pedestrian, okay, crosses now, but the traffic light has become green, but the agent knows that we still have to wait. And only when the path is clear will go. So this is not a matter of a sequence of if the light is green, go on, if there is a pedestrian break. So this all emerges. Okay, so here in this floor we have a movement in a driving simulator. The infrastructure, so the interface with the human. This was before when I arrived here in Trento, and we wanted to run a cover because this point were awful. And this seat was taken from a junkyard, scrapyard, yes. So it was kind of. We had some problem with COVID. We had to wait for pieces, but now finally we have this something. Still, we have some work to do because this arena uses 3 4K projectors with 3 dedicated computers with a 39 chip for each. And still, you can see they have like a crease here, and we are waiting for because we buy a proprietary software. Some guys from France have to come and do the blending process. I don't know how it's called, so we're still waiting for that. But for the rest, it's there. And since we spent so much money in this thing, we want to use many experiments with that. So first of all, I mean, can be you might think it's counterintuitive. We want to develop an autonomous agent. Why we want a person to drive? First of all, we want to get data about the way human drives, so we can actually evaluate how well the driving agent indicates the way they drive. Another thing, the main thing that we want to experiment with is this idea of distributed cognition. So the idea here derives from this horse ride metaphor. It's called pitch metaphor. Basically, this is a way to rethink completely the idea of autonomous people. So don't think about autonomous people in terms of the 5 levels that I told you before, but think about a system where the human and the agent collaborate on the time. Why is a horse rider metaphor? Because the idea is similar to what kind of collaboration happens between a rider and the horse. So if you think about both the rider and the horse are intelligent being, and the horse is able to move in the environment by itself. It's intelligent enough to know when there is a road, follow the road, and if there is a cliff, the horse knows to fall over the cliff. But what the human can do when riders ride the horse is to apply a bias to the action selection of the horse. So basically, with the reins, the rider can tell the horse to go faster, to slower, to turn to the right, to the left, and so on. So basically, we can imitate something like that in autonomous people. Only instead of using the reins, we can use the steering wheel and the pedals to tell the agent, for instance, to go faster, to slow down, and so on. The nice thing is that if you use an intelligent agent, the interaction is actually safe, because if the human tries to enforce a behavior that is not correct or meaningless, the agent will to discard that information. So, for example, if the human biases here the agent to go faster, so for example, pressing the gas pedal or steering to the left, the agent understands that he has to overtake. Here, since we have 2 vehicles and overtaking is not possible, even if the human tries to press the gas pedal, the agent will do nothing because there is no affordable action to execute. And of course, here, even worse, when the maneuver is actually feasible, but is dangerous and end up in a collision, even if the human tries to enforce that, the agent realizes that badly, so it will not perform that. This is an example with another software that we use to do simulation. So here the agent has a constant bias of going as fast as possible and then staying on the leftmost lane. In purple, you see the trajectory, the instantaneous trajectory decided. So here the agent sees there is a vehicle incoming. So even if the human enforces to stay on the left, it will go back to the right. And now he picks and see there is another obstacle. So oops, go back. And also this one is going more. And when lane is free, it will go back. And the last thing. Okay, so this is the last slide. Last thing, this most of our future work, we want to do some experiment on the simulator with the trolley problem. I don't know if you are familiar with that. It's a mental experiment. It's from the 60s, but it has now it became again popular because of many applications for driving. So basically, it's a situation in which there is a trolley car there are some technical failures. It is not able to brake anymore, and there is a the rail track divided into two, and there are 5 people, the first track, and 1 people here. The example is that these people will not see the trolley coming, will not have the time to run away. So for sure, the trolley will kill some of these people. You are here, and you can activate the switch. Normally, the trolley will go straight, so it will kill 5 people. If you flick the switch, the trolley will change the track and it will kill only 1 people. So the dilemma is here to cope with it. I mean, will you flick the switch and actively kill someone, or do nothing and kill 5 people? This is the dilemma. The idea in autonomous vehicle is what happens if there is children crossing the road so fast that I am not able to break the time, and the only way to not kill the child is for her to steer away and hit a wall. And I know if I will hit a wall, the people inside the car will die. So what the people, the agent should do? Save the child, kill the driver. Would you buy a car knowing that it will kill you in an emergency situation to save someone else? That's just an ethical problem. Just to close up, I remember there was one paper that was trying to solve this dilemma by doing some valuation on the hazard that the car will make. So you have this situation when you have 2 bicyclists. One is wearing the helmet and the other one don't. So the most safety, better thing to do is to hit the one that is wearing the helmet, because they will have a higher chance to survive. But then the fun thing is that that you're a cyclist, then I will never wear the helmet because I know that and with that I conclude. Sorry if I run late. Thank you.